Testing on YouTube. Testing on YouTube. All right, we're live on YouTube. Let's get a couple chews on that. Now let's wait for x.com. All right, it should be starting here momentarily. All right, I think it's live. It's live. Let me spit out my gum and then let's get started. Welcome everybody to another Hoopo stream. Hope you're having a great Saturday morning here. Today's stream is going to be called Vision Language Models. So we're going to be looking at a couple different papers and releases for new vision language models. We've done streams on these before, but you know these things keep getting better month over month. So we're going to see where progress is at right now. How's it going, Majetti? How's it going, Lit Guru? And how's it going, Amog? Amog with a question. Which deep learning model do you think is good for stock price prediction? So the way you phrase that question makes me think you're not thinking in the right way. So transformers, specifically large language models, are probably what you want to be using for stock price prediction. And even though large language models are a type of deep learning model, deep learning is a little bit of a outdated terminology to be using. How's it going, Josh? How's it going, Archon or Akdon? And how's it going, Ed and Khalil? Everybody. Josh, I've been poking at 1.6 lava this week. Definitely seems more powerful, but still held back by clip. Yeah, lava is one of the ones that we are going to be looking at. And actually, one of the interesting... Why don't we kind of go through the gauntlet of the different papers that we're going to be looking at. So first paper we're going to be looking at is MoE-LLaVA, which is a mixture of experts for large vision language models. So we've finally started to get a trickle of papers for mixture of experts, this time for vision language models. So you might have heard of mixture of experts for language models. I think the most famous one being the Mistral 8x7b. That model was really popular. Of course, the mixture of experts was predicted to be one of the core pieces of technology behind ChatGPT, because of mixture of experts is pretty good for batched inference and serving. But now people are using it for vision language models. There's another mixture of expert vision language model paper. This one is a little bit more of kind of like a deep dive on kind of the math and all the different types of routers and experts. And this one's called Routers in Vision Mixture of Experts, an empirical study from different people at Google DeepMind. Both of these papers are pretty recent, 29th January 2024, 29th January 2024. Finally, we got this one. This one's a little bit different, and I actually thought it was pretty cool. This one's called MoE, Polyvisual Expert Vision Language Model. So the Polyvisual Expert, we're going to see exactly what this says, but this isn't quite a mixture of experts. This is more using multiple visual encoders, kind of in an ensemble way. This one's also recent, 30th January 2024, from the Fudan NLP and Vision and Learning Lab. The last paper we're going to be looking at is Intern LMX Composer 2. Absolutely probably the worst name I've seen. That's a terrible name for 50 different reasons. Mastering freeform text-image composition and comprehension in vision language models. 29th January 2024 from a couple different academic institutions in China, and then also SenseTime, which is, I think, the really big computer vision company that has the contract for all the computer vision that the Chinese government uses in like their traffic lights and stuff like that, right? They have basically that fat government contract for that surveillance state situation. This one isn't quite a mixture of experts, but it does something interesting. It uses LoRa's, right? This low rank adaptation in order to basically fine tune the vision encoders so that they're a little bit more tokeny and semantic-y so that they can be used with these language models. So a little bit different from the other papers. And then there's two things that aren't quite papers that we're going to be looking at. So this is an interesting kind of new thing. Both of these papers, they're not even papers. They're basically blog posts, but they're kind of like papers. And it's interesting because we're starting to see, we have already started to predict this where like at some point people are going to stop doing these papers. These aren't even papers that are being published, like these are just going straight to archive. They're like preprints. The machine learning community is moving so quickly that kind of this format of papers is becoming less and less relevant. So kind of you're starting to see kind of what the new format would look like, and this is what it's going to look like. It's going to basically look like little blog posts like this where they kind of describe what's new in the latest version. This is LLaVA v1.6. LLaVA v1.5 is the one that most people are used to, and it's actually being used in a bunch of these benchmarks they're going to be comparing to LLaVA v1.5, but this is LLaVA v1.6. And then also in a similar kind of little mini blog post fashion, there's going to be the QuenVL, as in vision language, which is another Chinese vision language model. So that's going to be the different vision language models that we're looking at today. And why don't we start things off with a little bit of a benchmark? So I pulled up all the different vision language models that I could here. So we have a couple through Hugging Face, a couple through Replicate. We have ChatGPT, of course, Bard, and I'm going to be doing a little benchmark that I made up myself, and I've used this benchmark in a previous stream. But what this benchmark is it's a picture of Obama, except I cropped out Obama's face and I put in the picture of The Rock, which is another kind of celebrity here in the U.S. So the reason this picture is hard for vision language models is that vision language models take this entire image and then they tokenize it. They turn it into these patches and then they tokenize it. So pretty much everything in this image is screaming Obama, right? If you can think of like this image cut up into little squares, every single one of those squares is just telling the vision language model, this is Obama, this is Obama, this is Obama, this is Obama. And even the skin color of The Rock is very similar to the skin color of Obama, and like he even has like kind of the same kind of like smile lines and everything, and like the overlap, it's not super clean, right? Any human would instantly identify this as like, wait a second, this is not the same face with the thing. But for a vision language model, it's very hard, right? And so that's my little benchmark. And here I'm asking, for example, intern LM X Composer 2, and I'm like, who is this? And I give it this picture, and this is Barack Obama. Okay, so didn't quite get it right. Let's look at QuenVL Plus. Who is this? This is Barack Obama. Okay, still not getting it correct. Let's go to LLaVA. This is LLaVA 1.6 34B, which is the biggest one. So you can see here they have a 34B size. They have other sizes too. Who is this? This is an image of former President Barack Obama. Not looking good so far. We got Moondream 1. So Moondream is a very tiny little language model that someone in our Discord posted. And this one doesn't even get that it's Obama. It just kind of gives you some generic, this shows a man dressed in a suit and a tie, blah, blah, blah. Okay. We got, this is the same one, I guess. Probably doesn't matter. I could just close this one out. This is also LLaVA 1.6 34B, but this one's hosted on Replicate as opposed to Hugging Face. Take that out. This is ChatGPT. ChatGPT uses GPT-4 Vision, which is probably the state-of-the-art vision language model right now, and this one doesn't even give you an answer, so they give you the kind of AI safety kind of corporate, I'm sorry, but I can't identify people, blah, blah, blah. Kind of a non-answer, Bard, when you put it on Bard, it actually just removes the image, and then it says, how dare you post an image of a person? So 0 for 2 on the Corpo language model, vision language models. And then the only one that gets it is this one. This is Perplexity. And Perplexity doesn't use their own models. They use, for example, GPT-4 here. So I think this is GPT-4V, but this is the only one that gets it. And here you go. The image appears to be a digitally manipulated photo that combines features of President Barack Obama with those of Dwayne "The Rock" Johnson. The face is a blend of both individuals, blah, blah, blah. Okay. So there we go. That's my little benchmark, and maybe I'm going to have to figure out a new benchmark because it does seem like GPT-4V does get it correctly, but you have to be using GPT-4 Vision through a third-party provider such as Perplexity, because Perplexity doesn't have the same type of safety as GPT-4V and Bard. So I thought that was a kind of a cute little benchmark to start, just kind of showing you that the open source ones aren't quite there yet, but the closed source GPT-4V is there, but they have the problem of censorship, unfortunately. All right. Okay, we got some comments here from the chat. MoE shows that no expert is really an expert due to different experts at different layers. To me, it looks like an extra nonlinearity added in every FFN. Yeah, so mixture of experts, as we'll see, like they work better, but they kind of cheat a little bit. So here you see how here, rather than saying number of activated parameters or number of parameters, they use this activated parameters. So basically, mixture of experts have, here I'm going to be kind of jumping around here, but here's a figure 3 from the MoE-LLaVA paper. But here you have a standard kind of transformer block, right? You have your self-attention mechanism, you have your normalization, you have your residual connections going around here, and here you have, this is normally called the MLP, but an FFN. FFN stands for Feed Forward Network. MLP stands for Multi-Layer Perceptron. Both of those are basically same words for the same thing, just multiple layers of neurons that feed into each other. So MLP is the kind of more historically accurate name. I think it gives credit to the first person who made multiple layers of neurons like that, but FFN is also an accurate name. But in a MoE model, you replace a single feed-forward network, or MLP, with basically a mixture of these experts. So each one of these is basically like a little multi-layer perceptron. And then you add this extra piece here, which is called a router. And that router basically decides which expert to send it to, except it's usually not just one expert. It's basically a linear combination of a couple experts, known as the top K experts, where K is something like 2, right? And the reason that these mixture of experts are popular, one is because they are better performing, right? So you're literally adding more neurons, so of course it works better, right? That's kind of a no-brainer. But you can basically load them on servers in a way that's quite convenient. So whenever you're performing, you're serving models, right? You're a company and you're serving a model so that users can use it, and you have hundreds of users kind of sending requests for you to perform inference, right? One thing you can do is you can basically shard the model across multiple different GPUs, right? And one of these server racks will have 8 GPUs. So one kind of format that's pretty common is that these different experts are each on their own GPUs. So you can basically route into different GPUs, and that works really well when you have batches of user requests, because not everyone's going to be asking the same questions. So basically you can route different user requests into slightly different experts, and you get a good amount of utilization that way. But kind of going back to why I said this was cheating is that all these weights are still there, right? And here they say, oh, active parameters, but what they're talking about is that, okay, they only count the parameters that are being used. So all these other experts here, if they're not used during that particular inference request, then they're pretending that those weights don't exist, but they do exist, right? And if you only have one GPU at home, it's going to have to load that all the time, right? So it's actually very slow for a single GPU at home. It really only works well in these kind of like multi-GPU server setups. And here, whenever they say number of activated parameters, that's not really the total number of parameters, right? The total number of parameters is if you included all the experts, which would mean it would probably be somewhere around here, right? So they kind of use a little bit of wordplay and kind of like terminology sleaziness, I don't know how to say it, in order to pretend that they're here with the Mobile VLM 2.7b, right? They're like, oh, MoE-LLaVA 1.8b times 4. It's more than that, right? It's probably more around here. So it's really not that high performance for the specific number of, or the total number of parameters. It's just that now they kind of pretend that there's a difference between activated parameters and sparse parameters. Okay. So let's get to it. Let's start with, actually maybe instead of this one here, let's start with this one, because this one is a little bit more formal, and I think it gives us good definitions which we can then use for the other papers. So this is the DeepMind paper. Mixture of experts models are a promising way to scale up model capacity without significantly increasing computational cost. So here they're basically saying it's a bigger model, but you only ever use a subset of the parameters, so therefore you get a big model for a small cost. But again, what they're ignoring is the fact that you have to load those parameters into memory. So if you're doing this on one GPU, that kind of loading and unloading of different experts is very inefficient. It only really is efficient when you have a multi-GPU server rack kind of setup. The key component of MoE is the router, which decides which subset of parameters, which subset of parameters process which feature embeddings. So feature embeddings is just a kind of another word to say tokens. So basically they're referring to this, right? You have your router. Your router is getting basically what's coming out of this self-attention block here, right? So you're basically getting a bunch of tokens or a bunch of features, a bunch of vectors. And based on those vectors, the router is going to choose which expert to route it, or which expert's actually going to perform the feed forward step to then come up here and then go into the next block, right? We present a comprehensive study of different types of routers and MoE for computer vision tasks. We introduce a unified MoE formulation that substitutes different MoEs with two parametric routing tensors. So here they're basically going to create this unified MoE formulation, and what that means is that depending on which type of router you're using, you can formulate things differently. But when you're trying to do this kind of mathy theory type paper, usually what people will try to do is they'll try to say that, okay, actually these two different ways of doing routers are actually two different facets or different edge cases of a single unified way of representing router. So basically what they're saying is that we're going to introduce a more generic way of describing what a router is, and that generic way can then basically encompass all different types of routers that you see. So it covers both sparse and soft mixture of experts, where a sparse mixture of experts uses binary or hard assignment between experts and tokens. So that refers to hard assignment means that only one expert or only two experts are going to basically get the information and do that inference, and the other experts are going to get nothing, right? So it's basically zeros or one. The expert's either getting the information and doing something with that information, or it's completely zeroed out. That's called hard or binary or hard assignment. Soft mixture of experts uses a soft assignment between experts and weighted combinations of tokens. So soft assignment between experts and weighted combinations means that it might be going into multiple experts, but the output is going to be kind of combined, right? So basically, maybe this one gets a weight of 0.8, this one gets a weight of 0.1, and then this third one gets a weight of 0.1. So then the output is going to be 0.8 times whatever comes out of this one, plus 0.1 times whatever comes out of that one, plus 0.1 times whatever comes out of that one, and then maybe for the other experts here, the other 6 experts, you get 0, right? So you get like this extra weight. So you can weight what comes out of each of them and combine them, this weighted combination. Routers for sparse MoE can be further grouped into 2 variants. Okay, so token choice versus expert choice. So then within this sparse MoE, there's 2 extra not edge cases, what I'm looking for, variants, I guess. I'll just use the same word that they use. So you can either have token choice, which matches experts to each token, or expert choice, which matches tokens to each expert. So it's basically saying which kind of piece of information is deciding here. Is it basically the expert itself that's picking the tokens that it most wants to see that are coming out of here, right? Is there, this expert says, okay, well, out of all these tokens, I prefer these 6, or is it the tokens themselves that are basically saying, okay, well, I am this token, I am best suited for this expert, right? And that ends up having, it's a little bit more complicated because token choice versus expert choice, that also has to do with kind of load balancing and these kind of server setups. But here in this paper, really what they're trying to do is have this kind of unified mixture of expert formulation, which kind of encompasses all possible types of routers. We conduct head-to-head experiments with 6 different routers, so they're doing some good science in this paper. They're going to be basically doing a little ablation study for you where they try all the different routers and see which one works best, including existing routers and new ones we introduce. We show that many routers originally developed for language modeling can be adapted to perform strongly in vision tasks. So probably the router that they use in the Mistral paper will appear in here, but it's not, that doesn't really necessarily mean much. It's kind of like saying the transformer works well in language and it also works well in vision, right? It's like the router is not a very complicated kind of idea, so of course you're going to kind of see routers that work well in language also work well in vision. In sparse expert choice routers perform token choice, and then in soft MoEs generally outperform sparse MoEs. Okay, so soft MoEs outperform sparse, which kind of makes sense because they're a little bit more complicated, right? They're using this weighted combination coming from each of the experts. And expert choice outperforms token choice also makes sense because in expert choice, right, the expert picks the best possible tokens, but token choice is better for load balancing. So nothing, I guess, too surprising out of this paper. But the reason I want to go into this paper is because they have a nice little mathematical definitions for these. Let's kind of scroll through, see what else I highlighted here. Sparse MoE seek a hard binary token expert match. Soft MoE avoids the discrete, non-differentiable transforms often used in sparse MoE. So this is an interesting little tidbit here that I think is important, right? So sparse mixture of experts, right, pick one specific expert, right? They pick with a hard assignment, 1s and 0s, so 1, 0, 0, 0, right? They pick a specific expert. But the problem with that is that picking means you're putting in a hard 0 there, which means you're not going to really be able to push gradients through, right? And this being able to push gradient through, or the ability to take the derivative of it, right? Is it differentiable? Means you can take the derivative of it. Non-differentiable means you can't take the derivative of it. So a sparse MoE has this kind of hard binary assignment, which is non-differentiable, which means that if you're trying to push gradients into these things, you can't really be using sparse MoE. You want to be using soft MoE. So I thought that was a kind of important little tidbit to realize there. Thanks for the 11, Pratyush Kumar Sinha. I appreciate the contribution to the GPU fund. What is that large vision model released by Landing AI by Andrew Ng? I don't know. I don't know about it. If you post it, then maybe we can talk about it. Okay. We evaluate these models through few-shot transfer learning and fine-tuning on ImageNet. This is my one problem with this paper. So this is the DeepMind paper, right, which basically creates this unified MoE formulation and then does this kind of like ablation study over all the different types of routers and different types of decisions, architecture choices you can make there. But the problem that I have with this paper is that these two conclusions that they come to here, where, expert choice is better than token choice and soft MoE is better than sparse MoE, They come to the conclusion by evaluating the models through few-shot transfer learning on ImageNet. So ImageNet is really old. ImageNet is a classification problem where you're basically classifying images into one of some preset number of categories, say 1,000 different categories, such as dog, cat, tree, plane, car, things like that. So I don't feel like this is necessarily the best benchmark, right? I feel like if you're going to be benchmarking all the different types of routers and expert choice versus token choice and so on, I want to see a little bit more variety in these benchmarks, and benchmarks that are a little bit more modern and a little bit better suited for these vision language models, right? ImageNet classification is not, I think, a very good benchmark, but this paper does have very nice mathematical definitions, so that's really what we're going to be going to there. We let each expert be a multi-layer perceptron. So here they're basically confirming this, that each expert is going to be a little MLP. Here, again, they're calling it an FFN, but that's just an MLP. It's just two words for the same thing. So each expert is going to be a little MLP inside a transformer block inside a larger vision language model. So what is an MoE layer? So an MoE layer, you're going to have tokens, right? Each token XRD, where D is the dimensionality of the token, which basically means the number of numbers in that little vector, right? A token is just a little vector of numbers, and then the vector has length 1 by D. You choose K experts. That's how many experts you're going to be pushing into, right? In soft MoE, you're going to basically do a weighted combination of these K experts. In hard MoE, you're just going to pick the specific amount of K experts. So if you were doing hard MoE, or I think what they call it, sparse MoE. Yeah, sparse MoE with K equals 1 means only one expert is performing inference, and all the other ones are performing 0. All right, so your MoE is going to consume some token, right? Your MoE layer. What it's going to be doing is it's going to determine whether or not that token is going to go through that expert, right? So if you're doing sparse MoE, this is going to be 1 and then 0 for all the other ones. If you're doing soft MoE, this might be 0.9 and then another one might be 0.1 and so on. This MLP here, this is the actual multi-layer perceptron or FFN that's actually going to consume the token, right? So the token is going to go in and then it's going to come out. That's this little part here. And then the gate function, which we just described, basically just picks the expert for you, right? The top K expert. So here you're basically feeding in that token. Here you have the weights, you're adding some noise, and then you're basically picking the top scoring ones for that. So it's almost like a little mini classification problem into the experts. You have gating weights, linearly combine the output of E experts. E is the total amount of experts from which you're choosing K. The function top K sets all but the K less than or equal to E, so you want the number of experts that you pick should be less than the total number of experts, because then if not, then what the fuck are you doing, right? The whole point is to use a subset of all the total parameters, thereby selecting few experts for the combination. The gate parameters are trained in conjunction with other network parameters. Generally, you have to learn this router, right? You can't, the router doesn't just magically know. The router needs to learn how to route appropriately, and you can see here in the MoE-LLaVA paper. I keep going back to this one because this one has the best figure, but you see how here a trainable parameter is indicated by a fire. That means that that's going to actually be receiving gradients when you're training these models, versus the locked means non-trainable. So you see here, they're not actually changing any of the other parts of the attention or transformer block, right? Like the attention, the normalizations here, you're not actually changing any of that. The only thing that's receiving gradients here is the router and then the little MLPs that are each an expert, right? But whenever they say MoE layer, they're referring to this whole like pink part. So here, whenever they say an MoE layer, they're referring to that whole pink part, but then this MLP subset R here, that's the actual expert itself, right? So there's E total experts here. You're summing over all E experts depending on the gate, which is either going to be 1 or 0 or some weighted thing. The noise helps to improve the numerical stability of the router. This is the noise here. You just add a little bit of noise so that sometimes information gets potentially routed into the wrong expert during training. You know, get a little bit of noise in there. Okay. I don't know if I'm losing you guys or not. I'm a little bit afraid of doing 2 math sections in a row. So this is the unified formulation for what an MOE layer is. So any mixture of expert layer can be basically described as this. And then they also have further down an MOE router. Every single MOE router can be described as this, right? Why don't we go through the MOE router? I think this one's a little bit more useful. So an MOE router takes a mini batch input X T by D. So T is the total number of tokens, and then D is the dimensionality of those tokens, and yields the dispatch tensor DX T by E by C. So E is the number of experts, right? And then you have your tokens, and then what comes out is C, where C is the dimensionality of whatever comes out of these multi-layer perceptrons, right? Because you're feeding in these tokens, but then these multi-layer perceptrons have some dimensionality at the end here, and that's like the channel dimension, right? And that's the C there. The combined tensor, T by E by C, right, is the same, right, as this, same dimensionality, so that's when you combine them. If you're using sparse, you're going to be basically zeroing out all the ones you don't want and then just multiplying by 1 the one that you do want. If you're doing the soft, which means you're going to have weights, you're going to basically combine them. The dispatch tensor and the combined tensor are jointly referred to as the routing tensors. Okay, so not super important, to be honest. Like, this is just kind of like they go through every single possible type of expert, but I wanted to go through that first section there because I think that this was nice little explanation of what MOEs are. But now let's jump back into this one here, the MoE-LLaVA paper, because I think this one does a good job. Large vision language models. I don't like this. I prefer vision language models, VLMs. I don't know why people keep trying to make large vision language models a thing, LVLMs. Like, I prefer this, right? Let me see. This paper also says, this paper here, large vision language models, VLMs. I think that's just cleaner. Just VLM is so much cleaner than LVLMs, right? Like, I don't know. I don't like it. Scaling the model can effectively improve performance. Big models are better. Expanding model parameters significantly increases the training and inference cost, as all model parameters are activated for each token in the calculation. So here they're trying to kind of motivate why a mixture of experts, which only uses a subset of parameters for inference, is going to be faster. But again, I think this is a little misleading, because if you're performing inference on a single GPU, you're going to have to be basically loading things in and out of that GPU VRAM, which is quite slow potentially. We propose a novel training strategy, MOE tuning, which can construct a sparse model with an outrageous number of parameters. I got to give them bonus points for using the word outrageous, but a constant computational cost, and effectively address the performance degradation typically associated with multimodal learning. We present MoE-LLaVA, an MOE-based sparse LVLM architecture. This framework uniquely activates only the top K experts through the routers, right? So you're going to be basically picking the experts using that router, keeping the remaining experts inactive. Our extensive experiments highlight the excellent capabilities in visual understanding. Remarkably, with just 3 billion sparsely activated parameters, demonstrates performance comparable to the LLaVA 1.57b. And this is a little bit of the issue. So all these papers here, they're all going to be basically comparing to LLaVA 1.57b. So even though here they're saying, oh, it's better than LLaVA 1.57b or 1.57b and 13b, so therefore it's state of the art, it's not quite, right? Because this is 29th January 2024, and here LLaVA 1.6. So this field is just moving so quickly that all of these papers basically compare to the previous generation of models. So, you know, you kind of wish they would have compared this one to LLaVA 1.6, but it's like stuff moves too quickly. By the time they run the benchmark, there's already a better one out there. Is it possible to pay to use Lava 1.6 by API? Because I assume you can't run it locally. You definitely can. So you can just pay by API here, right? So replicate allows for that. And then also, here, if you go to here, you type in lava. Here you go. Lava 1.6 34B. There you go. You need to get a little replicate API token, and then you can just do it via API this way. And I think they tell you how expensive it is down here. So this model approximately cost about 0.2, so basically 2 cents to run on replicate, and it runs on an NVIDIA A100 80 gigabytes, which of course you don't have. But you can run probably the smaller one that I had here, Moondream 1. So this Moondream 1 is pretty tiny, and you can go here and run it locally on your computer via Docker. But the ones that are small enough to run on your computer with Docker are probably also way cheaper. You see how much cheaper this is? $0.0002 on replicate. So, unless you're going to be doing a huge amount of these inferences and you already have a GPU rotting at home that you paid for, it's probably just cheaper to use it via API. On Hugging Face, the way that you would do this, so here, let's do Lava v1.6 34B. So you can train, how do we do this? Auto train. I think you can, usually they have like inference endpoints. The problem with Hugging Face is that like they have so many different ways of doing things that it's starting to become kind of confusing to actually do anything with it. Let me see, Llama v1.6 34B. That's the one I'm on. Right here. Lava v1.6. I don't know. Sometimes these Hugging Face ones have like a Docker as well, so they have like a little option here where you can run it on Docker, and then sometimes you see these kind of like inference endpoints. Yeah, these things here. And these things allow you to basically run up your own server here on your dime, and then you can ping it. But yeah, you should be able to run some of these locally. Okay, let's get back to it. So we were here, we were looking at this MoE-LLaVA paper. Let's keep scrolling. We're going past the introduction here, and here in figure 2, they hit us with the illustration of the MoE tuning. So they're going to be training this mixture of expert models in 3 stages. So the first stage, they're only going to be training the multi-layer perceptron. In stage 2, all parameters are trained except for the vision encoder. And then in stage 3, the FFNs, or the experts, are used to initialize the experts, and only the MoE layers are trained. For each MoE layer, only 2 experts are activated for each token, so that K is going to be 2. So top K experts is going to be 2. This is going to be a sparse mixture of experts, right? So they're basically going to hard pick 2 and then not do any kind of fancy weighting or combination. I think the figure 3 here is a little bit more representative of the 3 training stages. I think this does a better, paints a better picture of what exactly is going on. So in stage 1, you're starting with a transformer language model, and you're starting with a vision encoder, and you're basically creating this little MLP here, right, which is sometimes called the adapter. It was called in previous papers. Now here they're just calling it the MLP. But basically what this MLP does is it modifies what comes out of this vision encoder, which is a sequence of vision tokens, right, because these are all transformer or vision transformer based vision encoders. And then it's going to adapt it such that it can basically be consumed by this language model. So they tell you what those are. So down here they say the specific vision encoder that they use is clip large, which is OpenAI clip large. And then the language model that they use, I had it highlighted somewhere, but I don't know where it is anymore. But anyways, so this stuff is all frozen, right? The language model's all frozen. The vision encoder is frozen. And in stage 1, they're only using generated text captions. So they're basically just using a data set here, stage 1 of training. They're using this LLaVA v1.5 data set, which is 558,000 images, so 558K images of just an image and then a caption, and an image and a caption, and an image and a caption. And by keeping everything frozen except for this MLP, what they're basically training this MLP to do, right, and by training what they're doing is they're basically pushing gradients down, is they're basically training it to adapt the vision tokens such that they become kind of text tokens, if you want to think of it that way. So that's stage 1. Then they do stage 2. Okay, so stage 2 training, now they're going to make it a little bit more complicated. Instead of just image and captions, they're going to be using images and responses. So this is a little bit more what you would expect from a vision language model, such as this is like an image response kind of thing, right? You have an image, you have a question, and you have a response. So it's a little bit more complicated data set, and they're going to be using specifically these 4 data sets here. So they're combining all of these. You have SVIT 157K, LVIS 220K, LRV 331K, where this number here is basically the number of examples. So you combine all of those together, you get roughly 964,000 examples of basically an image and then some response to the question that is being asked. And right, so here's the question that is being asked, here's the image. You're still freezing the vision encoder, so they're never pushing gradients into this OpenAI clip large. They're still here. They haven't frozen the MLP, so that's kind of interesting, right? They don't freeze this MLP. They just keep it training. Maybe they decrease the learning rate a little bit. But now they're also pushing gradients into this word embedding, which will kind of adapt. You see how now they're also pushing gradients into this language model as well, so into everything. So that's stage 2, right? Stage 1, just train this adapter. Stage 2, train the whole language model. And then finally we get to stage 3. So stage 3 of training, this is when they actually do the mixture of experts. And how do they do that? Well, they take your little feed-forward network, your little MLPs here, right? The MLPs that come out of this, you're going to have one for each of the layers, however many of these transformer blocks you have. And then you're going to copy them. So you're going to basically say, okay, I want 8 experts because my server has 8 GPUs in it. So I'm going to make 8 copies of this little MLP. And here are my 8 copies. And then I'm going to add this router. And now I'm going to push gradients with a data set that is, let's look at this last data set. The last data set for stage 3 is the LLaVA 1.5 mix 665K, which is 665,000 images of basically the same as stage 2, where you have instruction tuning request or instruction request, which in this case would be like the who is this, right? That's the instruction request. The image, which is the image of the Barack Obama, and then the response would be basically what comes out of here, right? So this text here. So that is what the last data set looks like. It's also what the second data set looks like. But now they freeze pretty much everything, and the only thing that they're pushing gradients into are these different experts here, which are all start exactly the same. So all of these are basically copies of this original one here. So initially, every single one of these is the same, but because you have this router, which is now routing into specific experts, right? And you're using a sparse MoE, where basically you're going to have some of them are fully used, and then the other ones are basically zeroed out. What's going to happen is that over the course of training, right, some of these experts are going to receive gradients, and then some of them are not. And then the next batch, the ones that aren't might receive gradients, and the ones that did not, right? So basically, this router in this stage 3 is going to result in each of these different experts here receiving slightly different gradients, and that's going to result in basically like speciation, right, or expertization. And what that means is that by the end of stage 3, these little experts here, they're no longer going to be the same weights. They're no longer going to be this anymore. They're basically each going to be slightly different versions of that, right? And then hopefully those slightly different versions end up being good at different things. Okay. Each token is processed by the top K expert with the highest probability, and the weighted sum is calculated based on the softmax of the probability. Here's your gate again. So I guess they are doing a weighted sum. So this is sparse assignment, but then within the two, they still weight it. So I don't know. I guess it's not true sparse, as they say here, right? Because in this paper, they kind of differentiate sparse and soft as sparse being hard assignment and then soft using weighted combinations. But here they're using a sparse in that only the top K are picked, but then within those top K, they're still using a weighted sum. So it's a little bit of both. We deploy an MLP to project the image tokens into the input domain of a language model, treating the image patches as pseudo-text tokens. So this is what they're talking about here, where the vision encoder, at the end of this vision encoder, you're getting basically a sequence of, I call them visual tokens, right? But they're really just visual or patches of the image, right? Where a patch is basically a little chunk of the image, and it's been cut and then fed through multiple layers of a transformer, right? That's what a vision transformer is doing, and then you end up with this little sequence of patches, but really they're visual tokens, I think is the better way to think about those. And that MLP just basically just morphs them just a little bit, just so that the language model here can consume them as if they were text tokens, or here they call them pseudo-text tokens. Okay, so that's the 3-stage training process that they use for this MoE-LLaVA. The loss here, relatively simple auto-regressive loss. So auto-regressive because here your response or your text caption, what's coming out of this mixture of experts vision language model is basically one token at a time auto-regressively. So you're looking at all the tokens that have been part of the prompt and then what you've already produced and then producing the next one, right? So for every single little token, right, where, for example, maybe this word here, American flag, why is this, right? Whenever it decides to produce this American token, it's auto-regressively looking at all these previous tokens and these tokens and the tokens that are coming out of the encoded image here. Okay. They do also have an auxiliary loss for encouraging experts to handle tokens in a balanced manner. This is important, and we've seen this before in other mixture of expert models. We saw this in the Mistral paper as well. So basically, what they're referring to here is that there's a loss for this router that basically tries to, it's called an auxiliary loss because it's like almost like a regularization. You're trying to add an additional or encourage a specific type of behavior. And the behavior that they want to encourage for this router is to kind of equally distribute the requests across these models, right? It doesn't, or across these experts. It doesn't want to just collapse and then just always pick the same expert every single time, right? Because then at that point, it's kind of pointless. So you have this auxiliary loss here, known as the differentiable load balancing loss, which basically encourages all the experts to get a little equal share. Okay, they use clip large for the image encoder, which we already saw. This is the data set, which we already saw. Here are the actual scores, so comparisons between different LVLMs on image understanding benchmarks. Here's your LLaVA 1.5, right? 7 billion parameter language model, 336 resolution on the image, so the image is 336 by 336. Here they say activated parameters, right? And this is the kind of cheat code that I keep saying where any of these mixture of experts, they keep pretending that only the activated parameters count, but it's like, no, the full thing counts as well, right? So it's like, anytime you download the model, you have to download all the experts. Anytime you perform inference on the model and the GPU and the experts don't fit in GPU memory, you're going to have to be loading those experts every single time per token. So I don't know, I'm still a little salty about this activated parameters kind of cheat code that they try to use here to pretend that 2.0 billion is way less than 6.7 billion, when really it's kind of about the same if you don't use this activated cheat code. But MoE-LLaVA 1.6 B4 top 2, hitting at 76 versus 78. It's not looking super good, guys. 50 compared to 37. Ooh. Ooh. It's only this one here, their bigger one here. MoE-LLaVA 2.7B times 4. I think the 4 means there's 4 experts total. Top 2 means the K equals 2, so it's the top 2 experts there, weighted combination of that top 2 experts. 3.6 billion parameters total activated, but if you account for all of the parameters, including the inactive non-top 2 ones, then it's going to be more similar to this, and it's just kind of, is it really that much better? I don't know. But does seem a little bit better. We need better benchmarks for these. I think there's too many benchmarks right now. Somebody needs to combine all these benchmarks and make like one giant ImageNet for VLMs. Okay. They perform particularly good on this object hallucination. So there's one specific benchmark that they use that measures hallucination, which is basically like imagining things in the image. And there they actually do perform better than, for example, any of these other ones here. But generally it's not good. Whenever people pick out a very specific benchmark like that, like object hallucination benchmark here, hallucination average performance, this is not performance on like 10 different benchmarks. This is performance on one specific benchmark. So I think this is kind of a little bit misleading as well, because it's basically you're picking out one specific benchmark that you performed very well on, and then you're basically saying, look, we're better than everybody else, and then there's little asterisks, and then you look at the little asterisks, and it's on this specific benchmark if you only use the activated parameters as the total parameter count. I think there's one more cool thing in this paper that's worth looking at, and that is this. So let me take a little sip of water. Max Argus. So the dense models are nearly always better. No, this is, I think lower is better. So you see here how the bold, or no, higher is better, sorry. Yeah, so here the MoE, this 61, that's the highest score here, right? This 43, that's the highest score here. I don't know why this 77 is the highest score compared to this 78. And that doesn't look good, especially considering that LLaVA v1.5 is not even LLaVA v1.6. So they're comparing to an old LLaVA v1.5, and it's getting a higher score. So, yeah, you're right. They do the same thing here. This is fucking misleading. Look at this, 61.5, bold. So, like, if you're just, like, kind of browsing over this, you're like, oh, look at that. This one here, bold, 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 bold. All right, I guess this one is the best, but that's not the case. Look at this here. MMGPT, 66. I guess that is the highest number there. 87 here. No, 85, 88. Okay, that is the highest number. Oh, here you go. 89 compared to 87. Yeah, not looking good. These guys are very crafty, And not to like generalize here, and I'm going to say some generalization here, but like this is papers that are coming out of different academic institutions in China, and like there's this concept in kind of Asian societies of like saving face, where it's like basically you always want to kind of present a very nice, clean thing forward, right? So for example, like anytime you buy a gift, it's like the box really matters, right? The wrapping of the gift really matters. And it's an issue in like politics too, because all the like low level kind of provinces, when they're reporting numbers up to the kind of like national level stuff, they cook the numbers, right? They cook the numbers because they'd rather cook the numbers and appear good than present the honest numbers and appear bad. So I think there's kind of a similar situation in these Chinese academic papers where basically they try to cook the numbers as much as possible, and not actually cooking the numbers. That's like, these numbers aren't made up, but like they present it in such a way that it seems like it's state of the art, but it's like there's like 10 different kind of like little like asterisks that prevent that, right? So for example, the hallucination, it's a specific benchmark. The activated parameters, well, that's not total parameters. And then even down here, as Max Argus even pointed out, like the bold is supposed to indicate the best score, but here it's not the best score, right? 78 is better than 77, 62 is better than 61. So it's a little bit unfortunate. I think it's just the result of kind of, like I said, just kind of a cultural difference there, and like the kind of expectation of performance, and like the way that kind of leads to this kind of like massaging of the numbers and presenting the numbers in such a way that you seem like you're getting something better. But okay, the one other cool thing that I wanted to show from this paper, and this is analogous to the there was a similar chart in the Mixtral paper when we went over that one, but here, distribution of expert loading. So basically, which experts are getting picked for each of the separate layers, right? So your language model here is where the experts are, right? And for every single layer or transformer block in your language model, you're going to have one mixture of expert layers. So that's what this here is, right? So here when they're saying MoE layer 1 all the way to 31, they're referring to the fact that this here, right, there's actually like 31 of these gray bricks on top of each other, right? So really, this would be MoE1, and then there'd be MoE2, MoE3, MoE4, and so on, right? And then why is there 4, expert 1, 2, 3, 4? Because these models are top 2 and then times 4, right? So the Mixtral is 7b times 8, which means there's 8 experts per mixture of expert layer, and you're picking, I don't know, I think the Mixtral one is softer, so it doesn't quite do this kind of hard assignment, but this one picks the best top 2 for each, out of 4 for each layer. But anyways, ultimately what they're doing here is they're basically feeding some data set through this, right? And when they feed the data set through this, they're saying, okay, well, which expert is consuming which tokens, right? So for example, what you would want this to look like is balanced. You would want, right, and you're encouraging that explicitly through the use of this differentiable load balancing loss, right? You're encouraging explicitly in the course of the fine-tuning and training for the expert, the router, to basically balance perfectly. And you can see that the experts kind of center on different things. Like for example, expert 3, this green one, tends to be active in the later layers, right? So it probably has a kind of some higher level abstraction versus the expert 2, this or expert 1, this blue one, really only active in the first couple layers, right? So it's kind of more of a low level, kind of high frequency type of expert, right? And then here, right, expert 1, 2, 3, 4, here they're saying text versus image. What they're referring to here is that some of these tokens, right, are going to be coming in through the image. So you're going to have your image is going to go through your vision encoder. It's going to turn it into a bunch of patches, then a bunch of visual tokens. Each of those visual tokens is then being changed by this MLP into a bunch of pseudo text tokens. And then you have your actual text tokens, right? So you have your actual text tokens, and then you have your pseudo text tokens, and those are being fed in here. And then you can say, okay, well, are the experts kind of specific to a modality? So is there one expert that only consumes the vision tokens and one expert that only consumes the text tokens? Because that would probably not be very good, right? And that's a problem with this kind of mixture of expert model that they allude to. Right here. The performance degradation typically associated with multimodal learning, right? So you have this over specialization, but that's not the case, right? So they do show you that it does seem like the experts seem to focus on both vision tokens here in image and text tokens. It's kind of interesting that they seem to focus more on the text than the image, which is something that people have noticed before. I think other times we've looked at vision language models, it seems like a lot of times it's not really looking at the image as much. It's almost more, it cares a lot more about the text than it does about the image. Okay. But that's pretty much it for this paper. They train this on 8 V100s with 32 gigabytes, so kind of big. You can't really train this at home. These are big data sets. This is like right around the edge, right? I think if you had a small academic lab, maybe you have a server rack or two. If you're a small startup, you might be able to do something like this, but this is not something you can train in your house. All right. Let's look at this one. This one's a little bit more of a throwaway. So we'll look at this one and kind of talk about what's a little bit different about this one, and then we'll go into this one here, this MoE. Actually, yeah, we'll do that. Let me take a sip of water, maybe answer a question or two. Okay, so this paper here, Intern LMX Composer 2, this paper is more about kind of creating basically an article entirely from a couple images here. So you see how they can feed in a couple images, and then they basically a little bit of text, and then they want to create a full, like an article that you would see on like a Substack or something like that, right? But the main thing that they really do in this paper that's different than the other papers is they use a LoRa, right? So in these papers here, right, they're using a MLP to basically take what's coming out of this vision encoder and then turn it into these kind of pseudo text tokens that can be consumed by the language model, right? In this paper, they do something a little bit different, and what they do is they have a LoRa that modifies the vision encoder, right? So they basically take the clip vision encoder, the OpenAI VIT large 336 clip model, blah, blah, blah. When used in conjunction with our partial LoRa module, a lightweight vision model performs effectively. For the sake of efficiently, we have to opt to use blah, blah, blah. So that's really kind of the only thing that they do in this paper that I feel like is worth noting. It's basically this, except rather than using this MLP here, they basically have a little extra LoRa. So that's how they're basically adapting the vision encoder for use in this vision language model. This proposed innovative partial LoRa approach, which is kind of interesting. I think in all the other vision language model papers that we've learned, it's almost always this little MLP here, call it the adapter, whatever you want to call it. But this is the first time I've seen that kind of like using a little LoRa instead, and just basically LoRa fine-tuning the vision encoder instead of creating this little new MLP layer that you fine-tune by keeping everything else frozen. So that's this one. And now I want to go into this one. So this one is a pretty cool paper. This one's called MoE Polyvisual Expert Vision Language Model. And why don't we just read the abstract here? Current large vision language models often encounter challenges such as insufficient capabilities of a single visual component and excessively long visual tokens. So here they're saying that when you take an image and you feed it into one of these OpenAI clip large, right? What's the number of tokens here is quite large, right? So when I feed this image into here, right, this image of Obama might be turned into 4,000 tokens versus this question here is like 5 tokens. So now you have this kind of imbalance where the amount of visual tokens versus the amount of text tokens is a little bit out of control. The issues can limit the model's effectiveness, inaccurately interpreting complex visual information, and overly lengthy contextual information. Addressing these challenges is crucial for enhancing the performance and applicability of VLMs. This paper proposes an ensemble of experts technique. So here they're using the word experts again, but this is not the same as the word experts here, right? So here the word expert is used to define a fine-tuned multi-layer perceptron that sits within a specific transformer block and that is routed to by a router little module. But here, what they're referring to by expert, and we're going to see, is basically they're going to use different image encoders. So rather than using a single image encoder as they do here, right, they just have one vision encoder they don't even push gradients into this. It's entirely frozen. You see how this is always frozen in all 3 stages of training. And then in this paper, this is the LoRa one. They don't keep it frozen, but they basically fine-tune it with a little LoRa model. In this paper, they have 4 different experts, more experts, right? So they use a bunch of different image encoders, and each of those image encoders is good at slightly different things, right? So they have the segment anything model, they have the clip image encoder. They're calling this a semantic expert. They're calling the SAM a segmentation expert. So it's a little bit, they're overloading the term expert there, but I think it's a pretty good idea. Synergizes the capabilities of individual visual encoders, including those skilled in image matching, OCR, image segmentation. So basically, right, vision encoders are good at different things. This technique introduces a fusion network to unify the processing of outputs from different visual experts while bridging the gap between image encoders and pre-trained LLMs. In addition, we explore different positional encoding schemes to alleviate the waste of potential positional encoding caused by lengthy image feature sequences. So here they're basically saying that whenever these vision encoders encode images into these sequences of vision tokens, they're also adding basically position information to each of those tokens. So actually, if we do vision transformer, I feel like we should have this image pulled up. But yeah, here. So open image in new tab. Right? When you are patchifying your image and then feeding each of those patches into the vision transformer, there's going to be a bunch of these blocks. You see here how there's a little position embedding, this 0, 1, 2, 3, 4, 5. That's a little position embedding, which is basically like a little piece of extra information that tells this transformer here, it's basically telling it where in this image is this thing, right? But think about that. Think about all this extra crap that you're adding, right? Do you really need that? And that's what this paper asks. They're like, hey, maybe we don't need to be spending all of this compute by adding all this extra positional encoding to every single one of these tokens. Addressing the issue of position overflow and length limitations. In our implementations, this technique significantly reduces the positional occupancy in models like SAM from a substantial 4096 to a more efficient and manageable 64, or even down to 1. Experimental results demonstrate that VLMs with multiple experts exhibit consistently superior performance over isolated visual encoders and mark a significant performance boost as more experts are integrated. So this was pretty good. Like, I think this paper, I like this one out of all of them. You know, we have kind of, this one is more like an implementation, or this one is the kind of more mathy DeepMind one where they kind of basically show you that all the different types of routers are really all the same type of router, but okay. This one here is more of an implementation type paper, right? Here's all the different data sets we use, 3-stage training pipeline. We're really trying to get state of the art, but we didn't even quite get state of the art. This paper here, the reason this is a great paper is because you can take this technique that they just did here and apply it to this one and get state of the art. You could apply it to this one and get state of the art. So this is something that I think we're going to be seeing more and more, right? This idea of basically multiple visual encoders or an ensemble of visual encoders. And look at these benchmarks here. So obviously they're not comparing to the most recent version of LLaVA, but this is LLaVA v1.57b, right? Better than all of that, right? MoE, more powerful. Obviously, it's going to be slower, right? The LLaVA model only has to perform inference for one vision encoder, so it's going to be faster and it's going to be less total parameters. But this one, you're going to have to feed it through multiple vision encoders, so it's going to be more parameters, but the performance is there, right? It is basically beating every single other one on every single benchmark. Here, what they're saying, single expert, double expert, triple expert, they're basically saying, okay, well, how many vision encoders do you use? Do you use only one vision encoder, such as the clip? Do you use two vision encoders, such as Dino and clip? Or do you use three vision encoders? And you can see that there's a little bit of a diminishing returns, but you do get consistently better scores on these benchmarks the more different types of visual encoders that you use. Triple experts are better than double experts, who in turn are better than single experts. Each model, with its unique approach to vision processing, contributes differently to understanding visual content. Right, this is the vision encoder. Clip, with its contrastive learning approach, excels in aligning images with textual descriptions, providing a robust semantic understanding. This is why Clip is always known as kind of the semantic vision encoder, because it's trained with a contrastive loss that has a bunch of language there as well. So basically the embedding manifold where your clip features live in is ordered in a very semantic way, right? So clip is the semantic vision encoder, is the important thing to remember. Dino V2, through its self-supervised learning paradigm at both the image level and the patch level, offers significant advances and robust and stabilized feature extraction without relying on labeled data. So Dino V2 trained differently from clip, right? Dino V2 is the one where it's like a picture of a goat and then the cropped in picture of a goat. So it's like a different loss, which means that over the course of training, you're going to end up with a different type of vision token, right? The representation that's coming out of the Dino V2 model is better at different things, right? So this paper is all about taking all the different types of vision encoders and then leveraging the fact that they're going to be good at different things, right? So they have a nice little description of the different vision encoders here. So clip learns image text alignment through contrastive learning. That's what the first C is. Contrastive learning, language image pre-training. Pre-trained on a large-scale data set, 400 million noisy image text pairs. The vision encoder of clip is a vision transformer with 300 million parameters. Output resolution is fixed to 336 by 336. Dino V2 is a student with a teacher where you have the more zoomed in and the more zoomed out thing. Patch level object applied to the extracted, blah, blah, blah. Dino V2 is a vision transformer with 1.1 billion parameters, right, compared to the 300 million of clip. So already that's, like that kind of tells you why this score is better, right? It's like, why does it beat every single other benchmark? Well, because rather than just using one 300 million parameter vision encoder, they're using a 300 million parameter vision encoder and a 1.1 billion parameter vision encoder and even more, right? So what are the other ones that they're using here? They're using the SAM, Segment Anything model, is a large-scale segmentation model which was trained on 1 billion masks, right? This is the one that came out of Facebook, pretty much the God tier segmentation model. It's going to be very, very good at like little details and edges. So actually, you know what type of stuff is important for this little benchmark that I did? The segmentation model, right? Because I bet you that clip, when clip visually encodes this image, it doesn't really, it's not really paying attention to this kind of like these hard boundaries versus something like the Segment Anything model. The segmentation is such like a pixel perfect kind of task that I bet you it would be like, wait a second, there's a fucking weird discontinuity here. What's going on, right? So maybe if this MoE model, they didn't have an easy inference on Hugging Face or Replicate or anything, so we didn't get to see it out, but I bet you probably would have solved that Obama benchmark that I created. So the SAM vision transformer has 637 parameters. But one of the problems that they run into here is that the feature dimensions, so the vision tokens that come out of clip, are 1024, right? So that's the dimensionality of the tokens, right? So if you remember back in our mathy paper over here, right, you have some tokens that are of dimensionality D. So the problem with using different vision encoders is that the tokens that come out aren't even the same size, right? Like look at this, 1024 versus 1536 versus 1280. Okay, so it's worth noting that each expert outputs a different number of tokens, and the dimensionality of those tokens is also different. So you're going to have to fix that, right? You're going to have to combine that, and that's where they're going to introduce this poly-expert fusion network. I feel like they should have just called it the fusion network. I don't know why they called it the poly-expert fusion network. That seems a little bit intense. But so you can see here they're feeding in the image, right? The words are going through a separate path. Then they're feeding in the image. They're feeding in the image into frozen versions. Here's the little frozen, which is the opposite of the fire, into 4 different experts here. The clip, the Dino. They also have Sam. They have some other ones too. Like they have Layout LMV3, which is apparently kind of good at OCR. But then you're going to end up with these different vision tokens here, and they're going to be not only a different number of them. So for example, the Sam vision encoder produces a lot more tokens, right? And they're bigger. So the dimensionality is wrong, and the number of tokens is wrong. And that's what this poly-expert fusion model is going to basically try to do. Is going to be try to massage that so that you can consume it correctly. So there's 2 different ways that they're going to try to do this. Actually, why don't we close this thread now that we're here. Given an image I in the input sequences and a vision expert encoder EI, we can obtain the representation of vectors in n image patches, assuming we have 3 experts. The final image sequence is a concatenation of the 3 output sequences. So basically, whatever comes out of each of these vision encoders, they're basically just going to concatenate it. So it's receiving a lot more, right? So not only is the number of parameters bigger, but it's also like the prompt is bigger. So the language model itself that's sitting on top of all of this is going to have to consume more tokens as well, right? And because it's autoregressive and quadratic with respect to the number of tokens, right? If you're adding just more tokens, it's going to take longer. But that's no problem. We got this poly-expert fusion network. The poly-expert fusion network, they try to do it in 2 different ways. So they try to use what they call MLP fusion, and then they use this Q-former fusion. This Q-former fusion, this is like the learned queries, and it's actually more complicated to understand than the MLP fusion. And if you cut to the chase, the MLP one is actually better, so we're just going to ignore this Q-former for now. Because this one is better. So how do they do this MLP? MLP, multi-layer processing, blah, blah, blah. Given a specific expert, the first layer is defined as MLP DI to D hidden. So here you go. This is how you get the dimensionality to match for the different tokens, right? So here, for each expert, you're going to have this little MLP here, and the output dimension of this MLP is going to be the same as the output dimension of this MLP here. Right, but the input dimension of the MLP here is going to be different than the input dimension here because this one has to deal with this expert and this one has to deal with this expert. So basically, you just put little MLPs to massage it. So actually very similar to what they did here, right? To whenever people first made a vision language model, they ran into this same problem where they're like, hey, wait a second, what comes out of this vision encoder is these vision tokens. The vision tokens aren't the same as these text tokens. How the fuck are we going to make them the same as the text tokens? Okay, let's make a little multi-layer perceptron here, and we can push gradients into it, and over time, the multi-layer perceptron will basically make these vision tokens similar to the text tokens. This is effectively the same kind of thing, right? You have these little MLPs. They try something a little bit more fancy here with this Q-former, but as I said before, it doesn't work better. They say it somewhere over here. Current mainstream open source VLMs only have 1 visual encoder that we already know. Why don't we just keep going? I feel like I'm skipping for no reason here. Okay, the different positional... Actually, let me see. Why do hackers wear hoodies? Because it's cold. You keep your house cold so your GPUs don't burn. And because you keep your house cold, it's cold, so you wear hoodies. Who is the person in this image? Pay attention to different parts of the image and come with a well-thought answer. Yeah, you could probably do that. I wonder if that works. Upload, Rockbama. Clear. Let's see. I'm going to copy paste your prompt here. Copy text. Actually, I'll just type it. Who is the person? Oh my God. Person in this image. Pay attention to the different parts of the image and come with a well thought out answer. All right, well, that's a terrible answer. Let's see if Quenville Plus gets it. Let's see if this one gets it. Quenville Plus, upload, Rockbama. Enter, submit. Come on. Come on. This person is Barack Obama. I'm telling you, man, it's not that easy. You can't just prompt engineer your way out of that. The problem is with the vision encoders. The vision encoders are basically just glossing over and losing that information, right? It's a lossy type of compression when you're taking an image and turning it into a sequence of vision tokens. Okay. But we were in this paper, the paper that has a bunch of different experts that are basically all producing their tokens. And then you have this poly-expert fusion network, which then creates a set of visual tokens that are more similar. But now you have this huge sequence of vision tokens from all these different experts. And like, it'd be good if you could reduce the total amount of numbers there. So how are they going to do this? So one thing that they're going to do here is they're going to say, okay, well, actually, like, we're spending all this extra memory and compute on all these different position encodings here. Why don't we just get rid of these position encodings? Do we even need these anymore? Visual experts already have position encodings. We believe that it is redundant to again assign a VLM position embedding to each visual token individually. So they're going to try different image, original, share all, share by row, and share by row and column. Among the four methods, share all can reduce the original O of n squared to O of 1, while the share by row and share by row and column can reduce to O of n. So basically, rather than having share all basically means all image patches basically have the same position embedding, versus share by row, share by column, you have basically the same column or the same row has the same position embedding. So at least in terms of the position embedding, the computational cost goes down. All of them can significantly alleviate the out of maximum length problem, but the question is, how much do they affect the performance? We report ablation results. Okay, so here's their 6 vision experts on 6 benchmarks. Here's if you do each expert individually. We're not necessarily super interested in that. Double vision experts. Let's go to triple vision experts. Triple vision experts. Okay, so if you use ConvNext, Dino V2, and Clip versus just Dino V2 and Clip, lose a little bit of performance. Gain a little bit of performance. Blue cells indicate the triple expert model is better. Red cells indicate the double expert model is better. Effect of fusion methods. Here's fucking the piece I was looking for this entire time. The results demonstrate that the MLP significantly outperforms QFormer in all cases, despite having fewer parameters and not utilizing a pre-trained parameter like the QFormer where it's learning these learned queries, right? So that's why I said skip over this QFormer, the MLP, which is not only simpler, less parameters, but it works better. Here's the real analysis. There was one other cool thing here. Yeah, this was kind of cool. So, effect of expert order. Okay, so the order of the expert matters. Due to the autoregressive and position-aware characteristics of an LLM, a different order affects the final output. And it's like, what? Well, think about it, right? So what they're doing in this paper is they're basically feeding in they're using additional vision encoders, but from the perspective of the language model, right, what it's getting is it's getting the caption or the request, and then it's getting a bunch of visual tokens. And then if you have more vision encoders, it's just getting more visual tokens. It's just getting basically a sentence, right? The LLM that's sitting on top of here, right, sees these as a sequence. So to the LLM, there is a difference between dark blue, light blue, orange, and red versus dark blue, red, yellow, orange, right? So like the order of the experts matters because the language model on top that's consuming them is reading them in as a sequence. So that's kind of a crazy thing to think about, right? Where Dino V2 into Clip is going to give you different performance than Clip into Dino V2, right? So this is kind of a wash. So you can see it doesn't really seem to matter whenever you have this one slightly better here, this one slightly better here, this one slightly better here. So depending on the benchmark, the order is good or bad, but that's kind of crazy to think about, right? Convnext into Clip versus Clip into Convnext. 61.9, 61.9, 86.1, 86.9. So like I said, the fact that it's 50-50 means it doesn't really matter. Basically, whatever you're interested in, which is some unknown benchmark here, right? Your benchmark, your task that you're interested in, it's going to be 50-50 whether this works better or that works better. But I just thought that was kind of interesting. And they actually have a little biological explanation with this. They say that phenomenon is also consistent with the characteristics of binocular vision, such as humans, where one eye is the dominant eye and the other is the non-dominant eye. The brain typically favors the input from the dominant eye when processing visual information. I don't know if I agree with this analogy. I think it's more like you're reading a book that has multiple images, and it's like, do they show you the one image first and then the next image, or do they show you the other image first and then this image, right? So it's like much like humans, right? Language models have this kind of recency bias where like the stuff here is going to be more. It's the order matters, right? It's basically it's consuming this as a sequence, right? And whether it's at the beginning of the sequence or the end of the sequence or the middle of the sequence is going to have a little bit of impact as to the final output. But I thought that was pretty cool. Effective different position encoding schemes. You see, it's not really that much. Share all is the best, right? The best in terms of computational efficiency. But this was interesting to me because it just means that maybe we don't need these positional encoding schemes, right? Positional encodings are very important in sentences, right? They're very important for text and language models. But when it comes to vision encoders, right, like VITs, it feels like it just kind of got added there because they were there already, right? It feels like we kind of just put position information into these VITs because they were there for the LLMs, and we're like, hey, well, it's also a transformer, might as well have vision, or might as well have position embeddings, right? But when I'm looking at these numbers, I'm like, maybe we don't need them. Maybe we don't need them in these vision encoders, especially if the vision encoders are then going to be fed into a language model for the purpose of a vision language model, right? And that would save a lot of, not a lot, but it would save a little bit of compute, right? So maybe if we just got rid of the vision position embeddings here on this vision encoder, you would save a little bit of compute and it would be better. So that's another thing in this paper that just like a little hint, a little tidbit that I thought was kind of interesting because it definitely had me thinking about like, wait, do we actually need these things? They do a nice little analysis here, and we find that their contributions in descending order are Clip, Dino V2, and Layout. So this is like Clip is the best, which makes sense. Everybody's using Clip, so this one uses Clip, this one uses Clip, right? All the other vision language models figured out that Clip is the best vision encoder because usually for a vision language model you want that kind of semantic information, but Dino V2 is basically the second best vision encoder, or at least it provides the most information that isn't already there with CLIP. New Image Gen 2 by Google, also worth looking. It'll probably be like this, though. That's the problem with the Google one, is that it'll probably won't let me identify Obama, because that could be dangerous. Okay. Data enhancement. Case study. How many horns are there in this image? There are 6 horns in this image. Okay. So those are the 4 papers. We can look at these a little bit. So I think this one's a little bit better. This is the blog post for LLaVA 1.6. So again, remember that pretty much all these papers have been comparing to LLaVA v1.5. So LLaVA v1.6 supposedly better. So we don't know if it's better than all these ones, but we know it's better than 1.5. They did a couple different improvements here. So they increased the input image resolution to 4 times. So now, rather than using the standard 336 by 336, right? I think they have that here. Yeah, if you look at LLaVA 1.5, the resolution of the image 336, resolution for this one 448, 224. So most of these vision language models use relatively small image sizes. So it seems like in LLaVA 1.6 now they have much bigger image sizes. So you should be able to get a little bit more detail. Better visual reasoning and OCR capability. OCR is the ability to read text from a image. Optical character recognition is kind of like a legacy term, to be honest. But they did that by having better tuning data mixture. So actually this model itself, this one used the LLaVA mixture here. So the LLaVA 1.5 558K, right? They actually have a better one now that probably has more OCR in it. Better visual conversation covering different applications, better world knowledge and logical reasoning, and efficient deployment and inference with whatever this is, SG Lang here. They're probably trying to promote this product. Okay. Open source LLaVA. They're open sourcing the code, the data, and the model. Don't let anybody else convince you. If you want a true open source model, has all of those 3, right? Meta says that their models are open source, but the only thing that they release is the code, and not even the training code. They only release the inference code, and then they release the model weights. But you need the data, and you need the training code. So I think that we should move to a world where you want all of these things available, right? The data is useful. The data is the most useful thing. The 34B variant finishes training in 1 day with 32 A100s. So if you have 32 A100s sitting around for a day, you could train your own state-of-the-art vision language model. You could just take LLaVA 1.6 and then you add extra vision encoders and you're set. There you go. That's state-of-the-art vision language model. Here's your results compared to GPT-4V proprietary models. So QuinnVL, Gemini Pro, these are all proprietary. And then you've got your open source ones. Pretty good. LLaVA 1.634B sitting at 51 on MMMU. What does that compare to this one? Do they have VQA? LLaVA Wild, Seed Image. Okay, like this is the problem. This is what I'm saying with these benchmarks is they're not even the same benchmark. I can't even like compare. MMB, is that the same one? MMVet? MMVet, here we go. Okay, we found a common benchmark. Okay, so on MMVet, LLaVA 1.6 gets 57.4. On MMVet, MoE-LLaVA 2.7b gets 31. That looks wrong. There's no way. 31 is terrible. Maybe, yeah, look at that. So LLaVA 1.5, 36. LLaVA 1.5, mixture of experts, 31. Still seems like it's probably a slightly different benchmark, or maybe the way that they're getting the score is slightly different, because that's another thing too, right? It's not the benchmarks themselves. Like there's different even within that benchmark, the way that you calculate the score is sometimes different. So you can't even really fully compare them that way either. But state of the art, 1.6. Pretty much it. They do this little trick. I thought this was kind of cool. We design our model at high resolution with an aim to preserve its data efficiency. When provided with high resolution images and representations, the model's capacity to retrieve intricate details is significantly improved. Right? So this is why they increase the image size as well. Our AnyRes technique is designed to accommodate images of various high resolutions. So the way that they do this is they have a grid. So they basically take your image, they cut it into 4 images, and then they feed each of those 4 images into the LLM. They also resize the image and then encode like the kind of grainier image and then feed that in. So you got kind of a more global representation of the information content in the image, and then you have kind of a more patchwise local information for each of the different parts of the image. And this is where, you kind of wish they took each of these pieces here and then fed them in to different vision encoders, right? And then you might get state of the art again, but it would be so much more compute, right? Because now you'd have to perform inference on your vision encoder 5 times for 20 times as opposed to just once. So we're starting to see that already, right? Even just in the natural language space, right? State of the art performance is basically how much are you willing to spend for inference, right? With chain of thought, like this type of stuff here, where you can basically use many different vision encoders, ensembles of vision encoders, ensembles of experts within the layers. Like, we're starting to see this clear relationship between getting state of the art is no longer the result of some fancy architecture trick. It's basically my pipeline performs 20 inference steps with 20 different models and then does that 10 times with a chain of thought, and that's how I get state of the art. So we almost need like a way to normalize that, right? We need like a state-of-the-art per compute budget. And even that would be very difficult to kind of quantitatively compare. But they scale the LLM backbone, so they make this part bigger. They make the LLM here, right? The LLM that consumes this, they use a bigger one. So which one are they using? Instead of using Vicuña 7B and 13B, they now use Mistral 7B and New Hermes Yi 34B. 34 billion parameter model. There you go. Lava 1.6 34B has this 34B New Hermes LLM. 303 million for the vision encoder, which they could have used more, right? They could have used Dino with the 1.1 billion and Clip with the 300 million, but the little connector, so the connector is the name for that little MLP here, sometimes also called the adapter. This little MLP right there. $558K, that's still the same amount as this. $558K. So they said they made the data set better, but they kept the same number in there. That's kind of weird, right? Here's your image size. So actually, they didn't actually increase the image size. So here they said they increased the image size, but really what they did is they basically just cut the image into 4 and then still use 336. So they're still using the OpenAI Clip model for the vision encoding, but they're basically feeding it like different parts of the image and then the resized image. 2-stage training procedure, stage 1 to train the connector, and then stage 2 to train the full model. So basically what they're doing here, right? Stage 1 to train the connector, stage 2 to train the full model, and then here they just have the stage 3 where they train the router and the experts. Pretty much it. This I thought was kind of cool too. So at the very end here, they talk about who gave them money, and you have A16Z Open Source AI Grants Program. A16Z is like a venture capital firm, And then you have Microsoft Accelerate Foundation Models Research. And you also have the Korean government. So it's like, what? Like, how are those three institutions, all three of them are providing money to this random vision language model? You know, it's like, don't you think they would want exclusivity over that? You know what I'm saying? Like, don't you think, like, A16Z would only give you money if you agreed to basically be a startup that was part of their portfolio? Like, why would A16Z agree to give money to people that are already getting money from the Korean government? I don't know. Weird. Okay, we got one last one here. We're kind of slowing down, and I apologize, but this is the last one. This is January 25th, 2024, introducing QuenVL, the Quen Vision Language. They have QuenVL Plus, QuenVL Max. Here's your benchmarks. Supposedly better than GPT-4V, but we don't really know much about it, right? As they say here in the LLaVA v1.6, it is proprietary. We don't know much. But here they say that, look at this, QuenVL Plus, 78 compared to 78 on Text VQA. QuenVL Plus is only at 45. They don't have text. Jesus Christ, dude. These benchmarks are out of control. Everybody's kind of around the same place. Like, I don't trust state-of-the-art for any of these. Everybody's pretending they have state-of-the-art, but nobody really knows what state-of-the-art is for these. It can solve stuff. It can write down what's on a license for you. Look at that. It solves this math problem. Can pick out the red car for you. That doesn't seem that difficult. Okay. That's pretty much it, guys. Let me sip some water, answer some questions, and then we'll end the stream. Anybody got questions? Anybody got questions? The model boasts a state-of-the-art marketing team. I think it's more a team lead that is afraid for their job. You know, they got to make sure that they get state-of-the-art, or they're going to get fired or not promoted. The same way that local government officials in China have to constantly pretend that they're doing way better than they are so that they can get promoted. Can we access this GitHub repo? Some of these have GitHub repos. Some of them do not. So obviously Quen doesn't. I think this one does. MoE does. A bunch of these have. You can usually find the GitHub repos in the paper. They'll link it. This one's kind of a nothing. Code is coming in 1 week, so you can check back. But you don't actually need this code for this one, right? Because this is a really simple concept. It's just combining a bunch of different visual encoders. I think the LLaVA models are the best. If you're interested in doing any kind of open source stuff, like these guys are the most open source out of all of them, and I feel like I trust these numbers more than any other numbers. So I don't know. I would recommend this one, the LLaVA 1.6, this code base here. 13K stars 3 days ago. Like, this is an active code base. Hey, good afternoon from Leon. How's it going? Does this model basically process images in a similar way to text? Kind of, yeah. It basically, what these models do is that they turn images into vision tokens, and then those vision tokens are adapted with this little multi-layer perceptron such that they become pseudo text tokens. We employ an MLP to project the image tokens into the input domain of the LLM, treating the image patches as pseudo text tokens. So basically, as far as the language model is concerned, it's basically consuming a sequence of tokens, and the tokens that come out of these vision encoders are kind of like tokens. The MLP is also called the connector here. So in this one, the terminology they use for that is connector. So you can see it's quite small compared to the vision encoder and then the language model itself, which is the big part, right? The language model is the part up here. This part. Boom, boom. I should just delete this gross highlight. There we go. This is the vision model, or language model. All right, let's summarize what we did. So, today's stream was called Vision Language Models. And in today's stream, we basically went over a bunch of recent releases in the vision language model space, kind of checking in, see how things are going, see what people are doing. And we got some new state-of-the-arts, and we got some new interesting ideas. So the first kind of idea that people are starting to do with vision language models is mixture of experts. So mixture of experts is something that people have been doing in the language and text space for some time now, right? Most famously, the Mistral 7B times 8, which uses 8 experts. Well, now people have started to do it with the vision language models, and this one's called the MoE-LLaVA 1.B times 4, so 4 experts instead of the 8 experts for Mistral. And what exactly is an expert? So if you're interested in the more formal mathematical definition of experts and routers, I would recommend this paper, which is by Google. But I'm mostly going to look at this figure, which I think is the best way to understand it. And basically what an expert is a multi-layer perceptron or a feed-forward network, which is usually there's just one per transformer block. But in a mixture of expert model, you're going to basically have many of these. In this case, 4, or in the case of Mistral, 8, right? But then once you have 8 of these, you're going to have to figure out how to route the inference into that specific one or some weighted combination of those, right? Where the specific type of routing can have a couple different types. You can have sparse routing, where you have a binary or a hard assignment between experts and tokens. You're picking specific experts. Or soft routing, where you're basically doing a weighted combination of different experts. So, yes. What else am I trying to say here? Okay, you have a mixture of experts. You're routing. The way that you have to learn these, you train these mixture of expert models in kind of a 3-stage process here. So the first step of this 3-stage process is simply the process of actually, the first 2 steps are how you get the vision language model. So once you do these 2, you have a vision language model. And then to make it an MoE vision language model, you have to do this 3rd step. In step 1, you basically have a frozen language model here. You have a frozen vision encoder here, such as CLIP. And then you're training this connector, this little multi-layer perceptron that takes the visual tokens, which aren't going to be the right kind of size for the language model, and they're not going to be the right, the language model's never seen them before, so it's going to need some help to kind of massage them into tokens that it can kind of understand. And that's what this little MLP is doing here, or connector. So you train that with a data set of 558K captioned images. Then in stage 2, you're going to use 964 and request response images, so images that have some question, such as how many dogs are there in this image, and then the response, there are 6 dogs in this image. And now you're going to be pushing gradients into the whole model. So you see how you're pushing it into the language model and still pushing it into the connector, but you're still not, you're never pushing it into this vision encoder here. But then you're going to get your vision language model at the end of this. Okay, so now you have your vision language model, which would just be your LLaVA 1.5 or your LLaVA 1.6, right? Just has a 2-step training procedure here. 558K to train the connector, and then 760K to train the full model. But in this MoE, they do one additional step where they basically take that little feed-forward network, this little MLP right here, they make 8 copies of it or 4 copies of it, however many experts you want to have, and then you have an additional little router that picks between those, and then you just push another data set through it. In this case, a 665K fine-tuning data set. And you're going to be pushing it with a pretty standard autoregressive loss, but you're also going to add this differentiable load balancing loss as a kind of a regularization or auxiliary loss that encourages the experts to handle tokens in a balanced manner, which basically means this little router tries to use all the different experts equally. right? So that's a mixture of experts vision language model. So these mixture of experts vision language models, they don't use all the parameters every time, right? They only use some subset of these experts, which means that technically the total number of parameters is not used at inference, which means that you can now create this new thing called number of activated parameters, where you're basically saying, okay, even though this model has 4 times 1.8b parameters, a little bit less than that, but 4 times 1.8b, we're going to pretend that it has 1.8b parameters because only some subset of those is activated. And I think this is a little disingenuous because this only really works like this if you're doing batched serving of this model on a multi-GPU setup where you have the model sharded on different GPUs, which is not the case if you're running this locally at home on a single GPU. At that point, the cost of loading and unloading these experts at inference per token, since you're doing an autoregressive VLM, that adds an additional overhead cost, right? So that additional overhead cost doesn't exist for these ones here, right? It doesn't exist for Llama Vid 7B or Chat UniV, whatever this is, 7B. Those, it's a, what they call a dense model, right? Even the word sparse versus dense is an overloaded term from kind of model sparsity, which is almost like a different thing, which is more about pruning and stuff like that. But a little bit confusing, but I think they're using a little bit of cheating here to make it look like their model is a little bit better than it is. But mixture of experts probably in general going to work well, especially if for these type of batched server type of requests, where you have a lot of user requests coming in at the same time, and you can kind of feed them in, and different experts handle a subset of the user requests. The experts that are being used equally, as makes sense, since you were training with this load balancing kind of loss or auxiliary loss. So you can see that different experts focus on different areas, different layers, so different depths inside that transformer. They focus equally on text and image tokens. So that's pretty good. You want to see that. In terms of the performance, it's not as great as you would want there to be. Obviously, they use less active parameters. So they're saying that, hey, for the same number or for less active parameters, we get roughly the same score. But I don't know. You know, it's not that amazing. You know, I feel like it would have been cooler if it did significantly better, but it just seems to be kind of okay. So that was that. This paper here does not use a mixture of experts model, but it does something interesting where it adds a LoRa to the visual encoder. So it basically, it doesn't train this little connector here. It adds a little LoRa to the vision encoder. I thought that was a kind of a cool little idea. This paper here, this was, I thought, the coolest paper that we looked at. This one's called MoE Polyvisual Expert. And in this paper, the TLDR is that they basically, they overload this term expert. So this is different from the word expert that we just saw. This now refers to different vision encoders. So they're basically going to be using not just clip. So all these other ones here, they all use clip as the vision encoder. This one here uses basically an ensemble. And it uses the vision encoder from clip. It uses the vision encoder from SAM. The segment anything model uses the vision encoder from Dino V2, a bunch of other kind of greatest hits of computer visions, right? Different models that have been trained over the years. Each of them has slightly different kind of visual representations, produces slightly different visual tokens. So those slightly different visual tokens are going to give you slightly different information. So then, therefore, if you feed all of the concatenation of all three of those experts, then you're going to get a better answer. The problem is that the visual tokens that come out of SAM and that come out of CLIP, they're not even going to be the same dimension. So you have to basically use this poly-expert fusion network, which is just like a really, really fancy name for what ends up being just basically a bunch of multi-layer perceptrons, so just kind of the same little connector type pattern. But this does perform better. It does perform better, and I think that this is another trick, much like the mixture of experts. I think we'll be seeing this trick more often than not. I think this idea of using multiple visual encoders we'll see that. I don't know if we'll see it in Lava 1. It's not in Lava 1.6, but I could see it in Lava 1. Maybe 2.0, maybe Lava 2.0, rather than using a single clip as the visual encoder, uses this kind of multi-visual encoder setup. The problem is, of course, that when you have multiple vision encoders, it's going to take longer to compute, not just because you have to feed the image into multiple vision encoders, but also because each of those vision encoders is going to produce vision tokens, and then you have to concatenate all these vision tokens, and then your language model sitting on top of that now has to consume a much longer prompt, right? So it's almost like you get 3-4 different things to describe the image for you, but now you got to consume 4 different descriptions of the image. And on that vein, kind of an interesting little tidbit that they found is that the position-aware characteristics of LLMs, right, the language models consuming this sequence, the order of the vision encoders affects the final output, which I thought is kind of cool. And it also means that the order of this probably matters too, right? I wonder if you put the word tokens at the end, it probably changes than if you put them at the beginning, or if you put them somehow in the middle, or you like interleave them in some weird way. I think there's probably some unexplored areas to research there in terms of like the ordering of these different tokens and the text and language there. They also do another little trick here, which I think could be interesting, where they take a good hard look at the position encodings. Position encoding is information that is usually fed into basically any type of transformer is consuming sequences. And whenever it consumes sequences, in this case, vision sequences from a sequence of vision patches, you're adding this additional position information via the form of a position embedding. But in this paper, they actually look at whether this is even required, and they try, for example, something as naive as just using the same position embedding for every single one, and it turns out that it doesn't really matter. So I thought this was interesting because to me it's a way of saving compute, right? If you don't have to add position encodings, position embeddings, each token is a little bit cheaper, everything becomes a little bit faster, right? Less stuff to chew through. So I don't know, this could be a canary in the coal mine for potentially the death of positional embeddings in vision transformers, but we'll see. Maybe it doesn't actually work well in the future. And that was pretty much it. We compared a bunch of different models. We fed them what I call the Obama benchmark. So this is a little benchmark that I came up with, where basically you have a picture of Obama, but I crop it out and put a picture of The Rock's face. And I love this benchmark for vision language models because it's like it's really tricky, right? The way that these vision encoders work, they're patchifying this and then they're turning this into these vision tokens. I think you're losing information that way, and it's very easy to lose the information of the fact that this guy's face is not even his face. So most of these vision language models will point out that this is Barack Obama, which is not correct, right? The only vision language model that did successfully get it was GPT, but it didn't even get it through the GPT OpenAI app, right? So if you actually put this in OpenAI, it tells you it can't help you identify real people. But if you do it through Perplexity, which uses GPT, then it does get it does succeed in this benchmark that it's a digitally manipulated photo. So we're getting there. I'm going to have to find a new benchmark. You know, my Barack Obama benchmark no longer works, but I'll figure out something else. And that's pretty much it, guys. That's where vision language models are at. I think they're getting pretty good. I think we can probably expect a mixture of experts. We can also probably expect this multiple visual encoder idea, although I guarantee you this poly expert name, that name is not going to stick. They're going to just call it multiple vision encoders. And in terms of which VLMs you should be using or fine-tuning, if you have any interest in that, I feel like Lava 1.6, it seems like it's the most open source out of all of them. Code, data, and model are open sourced, and everybody is using even their data sets for fine-tuning and pre-training. So that's pretty much it, guys. That's where vision language models are at. You can find all the links that I linked here on this GitHub page, streamdocs0302224. And if you're interested, tomorrow we're going to be doing a stream called Mobile Models, where we're going to be looking at a bunch of different models that are very small and tiny that run on your cell phone. If that's your jam, tune in tomorrow. If not, have a great day. MLPs are okay. Cool. Thank you, Pratyush Kumar Sinha. Thank you, GamerBG. Thank you, Josh Phillips, Yuhao, Majetti, Leon, Everygene. Who else? Atul, 87GN, Max Argus, Ayush, Huhu, Atul, Julian, Josh, Ed, Eclipse, Tarek, Amog. I think I'm getting everybody, but if I missed your name, I'm sorry. See you guys later, maybe tomorrow. Have a great Saturday.